The second part of the problem is deciding how to discretize continuous features. For example, if I have humidity being a real value number, how do I decide where to stop and create a partition to make another class? Because there's an infinite number of places to split the real valued number line, how would we do it? It's clear that one part of the problem is solved by understanding that moving the split point between two observed values usually has no effect on the information gain. So whether I choose C1 or C2, which are both between this red point and this red point on this one-dimensional part for xj, won't help change what we want to do. So we can just choose the midpoint between these two for best generalization. And we can also see that splitting only between examples from different labels y would be optimal for information gain. If we split within a class, as we have done in the previous line, for example C1 and C2, there is no difference in the classification value. They're both red. So we should choose to split only between cases where the labels y change. In this case, if we have a binary classification problem where the positive examples are green and the negative ones red, the only admissible places where we should try to think about are between here and here. Using these two criteria together, we can create a candidate place to split the feature. A final question that we're going to study more in our in-class activity is where we decide to prune back a decision tree that's fully grown. Our answer for now is to use validation, meaning that we go through a training and validation phase, and when we remove nodes in the decision trees that are closer to the leaf going upwards towards the root, we're going to see whether they can be replaced by the mode of the labels at that point. And if the prune decision tree actually works better in the validation set over the training set, we're going to cut and replace that node. We can do this recursively to prune back multiple layers of the decision tree until we have a good fit. In summary, we can understand and analyze the decision tree learning algorithm. The good is that this model is very interpretable and intuitive, especially helpful for data exploration when we're doing machine learning in the initial exploratory period. It's very efficient because at training time it's executing a greedy search, and at testing time it's just applying different logical tests and reaching a conclusion for each individual training example. And similar to support vector machines, it discards information to make a generalization. Unlike support vector machines that discards instances, decision trees only look at one feature at a time, discarding all of the other features as irrelevant for the particular logical test that it's carrying out at a level. It does this through the use of information gain. However, there are also some bad points. It has a bit of instability because each of the decision trees that are learned can be very specific to the training data, and so will have high variance, and is very susceptible to small fluctuations in the data. It's also the case that the decision boundaries learned are hard decisions. By default, there are no ways of probabilistically interpreting the boundaries, although there are extensions for doing that. And that unlike all of the other linear models which we've looked at, because the decision tree makes axis perpendicular decisions, it doesn't capture the interactions between features. If there are useful features that need to be engineered to make the decision, they need to be independently engineered and introduced into the dataset before running decision trees.